All right, good afternoon, or good morning, technically still, lads and ladies. Welcome back to Honors Calc 1. Today, we're going to talk about a really cool section. Unfortunately, it's something that the topic we're going over here takes a while. Each one of these problems is fairly involved, and especially today, since it's the first time we're going to be going through it, it's going to be a minute before we get to any of the problems. And it's somewhat unlikely that we'll be able to do more than one. What I am going to do for you guys is do a different set of examples than what I did for my first class, so you can watch the video from my earlier class to get one worked example, and then the one we're going to do today will be different. That way you get some variety. I noticed this morning that the last two videos that I posted to YouTube haven't come over to Canvas yet. That's my fault. I'll get those linked up and sorted out today. Today is the 1st of March, 2021. And the section we're covering today is one of my favorites, curve sketching. The good news about this section is that it doesn't actually have anything new. It's all stuff that we've seen before. But we're putting together everything that we've been talking about for the last couple weeks. So it's worth talking about on its own, and there's a kind of procedure or algorithm here for getting this done that I wanted to share with you guys, and I think it's important. So, is there anything else I want to say? Oh yeah, note. As you solve the 4.5 problems in this week's homework, it is critical that you sketch the graphs by hand. Like I do today. It's a funny thing, you know. WebAssign tracks how long a student spends on average on each problem. And when I look at those statistics for the problems in section 4.5, they all say like 2 minutes, 3 minutes, which is fucking ridiculous because these are really long problems. The reason, of course, is that WebAssign presents you with a collection of like 4 graphs and you just have to pick the right one and it marks the problem as correct. That is not solving the problem. I want to be really clear about that. The point here is not clicking the right graph. The point here is drawing the graph and then matching it to the one that they present you. If you just go through, click the right graph and move on, you are not going to get what you should be getting out of these problems, not even close. So please, as you solve those problems, do what I'm doing today. The other thing, of course, is that the L'Hopital's rule problems are on this week's homework. I didn't want to overwhelm you guys last week. So all the L'Hopital's rule stuff from Hannah's lecture on Friday, those are on this week's homework as well. Okay. So how to sketch a good graph of the curve y equals f of x. And this is section 4.5. First, find the domain. We need to know the domain to know whether any of the things we find later are critical numbers or not. Remember, the key to doing this is to watch out for red flags. The red flags are variable stuff in the denominators. Of any fraction, right? You know the bottom is not allowed to be 0. The second thing is variable stuff under an an even root, like the, if you have some stuff under an even root, then that stuff needs to be greater than or equal to 0. And the third thing is variables inside logarithms. Inside the natural log or some other log. The inside needs to be strictly greater than 0. So your first step is going to be to find the domain. The second step is going to be finding any intercepts. Y-intercepts, to find these, you just plug x equals 0. To find x-intercepts, we need to solve the equation f of x is equal to 0. And if your function happens to be a big fraction, solving f of x equals 0, you can just set the top equal to 0. Part C here, your third step, is going to be to look for any symmetry. And there's three big ones. You've got even functions. So I'll organize these by the symmetries, I guess. Y-axis, symmetry. This would mean you have an even function. And to find this, you check whether f of negative x is the same as regular old f of x. There's origin symmetry. This corresponds to odd functions. And to check if your function is odd, you look whether f of negative x simplifies to negative f of x. And then the last thing is periodicity. Is your function periodic? Sorry. If so, find the period. These are all ways to just make life easier, right? If your function has y-axis symmetry, then you only need to graph half of it. And then to get the other half, you just reflect that, right? You don't actually have to go through all the work to graph the other side. Or if your function has origin symmetry, then you can figure out the graph on the right half and then reflect that through the origin, and that will get you the left half. And if your function is periodic, just find the graph on one period, and then you have to just cut and paste. The next thing you're going to look for are asymptotes. Vertical asymptotes. You know that f of x has a vertical asymptote at x equals c if the limit as x approaches c of f of x is 1 of plus or minus infinity. So you're looking for places where the function blows up to infinity. And then horizontal asymptotes f of x has h a y equals c if lim x to infinity f of x equals c, or lim x to negative infinity f of x equals c. And these are mostly things that we teach algebra students how to do, you know, finding domains, intercepts, even and odd functions, and vertical and horizontal asymptotes. We don't talk about asymptotes in the language of limits in those algebra classes, at least not usually, but we do teach all this stuff. This should all be familiar even to a strong pre-calculus student. The really big new stuff comes from the next few things, which all have to do with the first and second derivatives. So are there any questions or anything that you guys would like to ask about before I move on to the kind of E through H stuff? I should have a question mark here. Is your function periodic? Okay. So item E here is to find intervals of increase and decrease. And item F is to find any local mins or maxes. And these both come from the number line for the first derivative, f primed of x. The last thing that the book lists here is to find intervals where fx is concave up and concave down, and any inflection points. And this comes from the number line for f double primed. And then kind of cutely, the last thing here is just sketch the graph. I would add here, make a number line for the shape of f. And maybe plot a few extra points. So the kind of high-level thing that's going on here is that when Desmos or a TI-84 or something like that goes to graph a function, it makes a massive, massive table with thousands and thousands and thousands of points, and then it just plots all those points. And it has so many points that it actually looks like a curve. We, as human beings, with our tired little hands, don't want to do that. It would take us way too long. So instead, we run through this algorithm. And that will kind of tell us the shape of the graph on a bunch of different intervals, and we'll have a few points, and we'll kind of connect those points with the appropriately shaped pieces of curves. And so instead of plotting 10,000 or 100,000 points to get a decent picture of the graph, we just have to plot a few points and then draw the appropriately, you know, increasing, concave down, whatever curves. So that's what we're going to do. The example that I did in my first class this morning was 2x squared over x squared minus 1. And I'll post both of the videos, this video that we're making right now and the video from this morning, so you guys can watch me working through that with them. But for you guys, I want to do something else, and that way I can share this with them for a second example, because these really do take a little while. So I'm going to say here, follow the guidelines. To sketch the graph of f of x equals x times e to the negative x. So we want to find domains, intercepts, asymptotes, symmetry, and then increasing, decreasing, mins and maxes, concave up, concave down, inflection points. And once we have all of that, then and only then will we attempt to sketch our graph. Everybody on board with what we're trying to do? This is how human beings draw good graphs, right? Not computers. This is how humans do it. So first we find our domain. There are no red flags here, right? No variables downstairs. If you wanted to, you could say, well, e to the negative x, that's 1 over e to the x. So we need to make sure e to the x is non-zero. But if e to the x is equal to 0, then you take the natural log on both sides, and you would get x equals the ln of 0, which does not exist. So yeah, no domain issues. Our domain is negative infinity to infinity. Intercepts. To find my y-intercept, I plug x equals 0. That looks like f of 0 is 0 times e to the negative 0, which is 0 times e to the 0, which is 0 times 1, which is 0. So my y-intercept is the point 0, 0. X-intercepts, I solve f of x equals 0. And that's the same as saying x times e to the negative x equals 0, which is the same as saying x over e to the x is equal to 0. And then if you kind of cross multiply, you find that x is equal to 0 times e to the x, which is the same as just saying x equals 0, because e to the x times 0 is 0. So my x-intercept is also my y-intercept. There's only one intercept, it's the point 0, 0. All right, and if you want to, you can like keep track of these things as we go, so they're easy to find when we look back for them later. My next move is to look for symmetry. So to do this, we replace x by negative x and see what happens. Here I get negative x times e to the negative of negative x, which is negative x times e to the x. And this is neither f of x nor negative f of x. So f is neither even nor odd. And of course, this is not periodic. No trig stuff. So this is not periodic. So there isn't, unfortunately, any symmetry here that's going to help me out, but that's okay. I can look for asymptotes. The vertical asymptotes, I would be looking for places where f of x is undefined, right? I would need to find places where this blows up to infinity, but this is never undefined. So there's no vertical asymptotes. I want to look for horizontal asymptotes, I have to look at the limit as x goes to infinity of f of x, which is the limit as x goes to infinity of x times e to the negative x. And this is precisely why we had to talk about L'Hopital's rule before we could do this. This is why we had Hannah's lecture before 4.5. If I try to plug in infinity here, this looks like infinity times e to the negative infinity, which would be infinity, oh shit, I gave it away, infinity times 0. And that's indeterminate. So I have to rewrite this as lim x to infinity x over e to the x. And now this looks like infinity over infinity, so I can use L'Hopital's rule. And I get lim x to infinity 1 over e to the x, which is 1 over infinity, which is 0. I also need to look at the limit as x goes to negative infinity. Maybe this has a different horizontal asymptote on the other side, like the arctan function. So lim x to negative infinity here of x e to the negative x, what does that look like? Well, that's negative infinity times e to the negative infinity, which is negative infinity times e to the positive infinity. And e to the positive infinity is infinity. So this is negative infinity times infinity. That's not indeterminate. That's just negative infinity. So my asymptotic behavior as x goes to positive infinity, y goes to 0, and as x goes to negative infinity, y goes to negative infinity. This is how I would keep track of the asymptotes. So I do have one horizontal asymptote. It's the line y equals 0, and I only approach it on the right. As x runs off to the left, y just blows up down, like negative. Part E is where things start to get good. Intervals of increase and decrease. And part F, mins and maxes. We do these together. We do these by building the number line for f primed. So here, f primed of x is the derivative of x times e to the negative x, which is a product rule derivative with a little chain rule thrown in. This is the derivative of x, which is 1 times e to the negative x, plus x times the derivative of e to the negative x, which is e to the negative x times negative 1. That last bit there being the chain rule. So it's a product rule, right? U prime times v plus u times v primed. If you call this, if you want the details here, here's u and here's v. This is u primed times v plus u times v primed. This whole piece here being v primed. In order to make my number line for f primed, I need to find the critical numbers, blah, blah, blah. So in order to do that, I need to simplify my derivative. This is e to the negative x minus x e to the negative x. I can factor out the e to the negative x. I get e to the negative x times x. Oops, sorry, I'll do it over here. If I factor out the e to the negative x, I'll get 1 minus x times e to the negative x. So my critical numbers, this is where f primed of x is equal to 0 or undefined. F prime will be equal to 0 when x is equal to 1 from this factor. All right, if you set 1 minus x equal to 0, you get 1 equals x. So that's one of my critical numbers. F prime is never undefined. All right, this is a polynomial times an exponential. So he's always happy. So on my number line, I only have one number to put here, 1. And to the left of 1, I could test x equals 0. F primed of 0 is 1 minus 0 times e to the negative 0, which is just 1. In particular, this is positive. So f is increasing. And over here to the right of 1, I could test x equals 2. F primed of 2 would be 1 minus 2 times e to the negative 2, which is negative e to the negative 2, which is negative. So over here, f is decreasing. E to the negative x is never equal to 0. That's something that we verified earlier when we were looking at the domain. If you remember, you're right that normally we should, right? We normally would set all the factors equal to 0. But we saw earlier that if we try to solve e to the x, here, e to the negative x equals 0, here, I'll write it down. You're right, I'm technically being a little bit sloppy here. Where can I fit this in? And e to the negative x equals 0. This has no solutions. If you were to take natural logs on both sides, you would get negative x equals, so negative x equals ln of 0, which would mean x is negative ln of 0, but this does not exist. I don't know, you guys probably couldn't see that, but Katie asked, why, well, you know, what about this other piece, right? If our derivative is 1 minus x times e to the negative x, we should be setting each factor equal to 0 to find out where f primed is equal to 0. She's right. Setting that first factor equal to 0, we get 1. And if you try to set the second factor to equal to 0, you'll find that it has no solutions. Because to solve this equation, you would take the natural log on both sides. And that would give you on the left negative x, and on the right the natural log of 0. So x would be equal to the negative natural log of 0. But ln of 0 doesn't exist. So yeah, e to the negative x is never equal to 0. But it's a good thing to look out for. You're right that we should check. So now I know where f is increasing and where f is decreasing. F of x increases on the interval negative infinity up to 1, and f of x decreases on the interval 1 to infinity. There's something else that we've learned here also. If I'm increasing, decreasing, what must be going on at 1? What's happening right here at 1? If I'm going uphill, and then downhill, what kind of feature exists on the graph at x equals 1?
Local maximum.
Yeah, it's a local max. So we have a local max at x equals 1, and we should find that local max value. The max value is f of 1. And if I plug 1 into the original function, I get 1 times e to the negative 1, which is just 1 over e. So that is all the increasing, decreasing, min and max stuff. Now I need to take my second derivative. Before I move on to the second derivative, are there any questions about the increasing, decreasing, min and max stuff? Okay. So f double primed. Now we're moving on to concavity. This is technically, I think, part G. I'm just going to say concave up versus down, and inflection points. F double primed we find by taking the derivative of f primed, which is the derivative of 1 minus x times e to the negative x. And that is, again, a little product rule derivative. I'm going to come back over here to do it. Maybe I'll write this one out schematically. So this is 1 minus x primed times e to the negative x plus 1 minus x times e to the negative x primed. The derivative of 1 minus x is negative 1. So I have negative 1 times e to the negative x plus 1 minus x times the derivative of e to the negative x. That is e to the negative x times negative 1, just like it was before. It's a little chain rule thing. So if I distribute everything out, this is negative e to the negative x, and this is so minus e to the negative x plus x e to the negative x. You can think about like this is negative e to the negative x, and I'm going to distribute it here and here. So altogether, this is negative 2 e to the negative x plus x e to the negative x. And if I factor out my e to the negative x, I get negative 2 plus x times e to the negative x. So f double primed of x is equal to 0 if negative 2 plus x equals 0, or e to the negative x equals 0. Again, this never happens, but this one will happen if x is equal to 2. So on my number line for f double primed, I again just have one number. And this time it's 2. I can test x equals 0 on the left. If you plug 0 in, f double primed of 0 is negative 2 times e to the negative 2, e to the negative 0, which is just negative 2. So this is negative. And then to the right of 2, I could test x equals 3. And f double primed of 3 would be negative 2 plus 3 times e to the negative 3, which is just 1 times e to the negative 3. And that's a positive number. right, that's 1 over e cubed. So this goes negative, this goes positive. So I am concave down. F of x is concave down on the interval negative infinity up to 2 and concave up on the interval 2 to infinity. And we have an inflection point at x equals 2, right? That's where the concavity changes. The point here is 2 comma f of 2, and f of 2 is 2e to the negative 2. And if you want, that is that's 2 times comma 2 over e squared. E is pretty close to 3, so e squared is pretty close to 9. So this 2 over e squared, it's a small number. And this is all the stuff we get from the second derivative. Now we have everything we could possibly want. So we're going to come to our last step where we create, sorry, I'll hold here for a second. Anybody needs to get stuff down. I know where I'm increasing, decreasing, and I know where my mins and maxes are. I know where I'm concave up and concave down. I know where my inflection points are. I know all the asymptotes. I know all the intercepts. So I'm ready to graph this sumbitch. So my last step, I am going to go ahead and turn the page now. If you need a screen cap or anything, go ahead and take it. My last step before actually drawing the graph is to make a number line for the shape of F. And on this number line, I'm going to put any x value that was on any of the previous ones. Now there are only 2, 1 and 2. Now we look back at our previous results. From, where is it? It's over here. From negative infinity up to 1, I am increasing. And I'll not have this somewhere I can write them both down. I don't. All right. From negative infinity to negative 1, I'm increasing. And from negative infinity up to 2, I am concave down. So increasing and concave down everywhere to the left of negative 1. So if I'm increasing and concave down, that means the shape of my graph there is like this. What about between 1 and 2? Well, all the way up to 2, I'm concave down. But at 1, I switch from increasing to decreasing. So from 1 to 2, F is decreasing. But we're still concave down. All right, F double prime is negative. So if you're decreasing in concave down, that looks like this. From 2 to infinity, 2 is definitely to the right of 1, so we are still decreasing. But at 2, we switch to being concave up. So here we are still decreasing, but we switch to being concave up. And decreasing concave up, that looks like this. All that work from parts what are they? E and F go into making this number line. Now here we know that this means we have a local max. And that point we found that was 2, 2e to the negative 2. And here we had an, oh wait, what was the local, no, that was the inflection point. I'm sorry, what was our local max? It was at 1 comma 1 over e, I'm sorry. 1 comma e to the negative 1. And over here we had an inflection point, an IP, and this was at 2 comma 2 e to the negative 2. And this number line contains all the stuff that we need to draw our graph well, as long as we remember domains, intercepts, symmetry, and asymptotes. So now we're ready to draw our graph. All right, I'm going to mark 1, and I'm going to mark 2, because I know that important stuff happens there. The other things that we learned that were important were these asymptotes, right? We know we have an x and a y intercept at 0 here, so I'm going to plot that. And I know that as x goes to infinity, y goes to 0. So I have a horizontal asymptote y equals 0 over here that I'll plot. Now to make my y scale here make sense, I think it's worthwhile to think about how big these numbers are. E to the negative 1 is about 1/3. E to the negative 2 is about 1/9. So this is like 2/9, and this is like 1/3 or 3/9. So I would, make 1 be like way up here. My local max is at 1 comma e to the negative 1. So that's like 1 comma 1/3. It's like here. And my inflection point is at 2 comma 2 e to the negative 2. That's about 2/9. So a little bit less than 1/3. And I know that as x runs off to the left, as x goes to negative infinity, y goes to negative infinity also. So I know that my function is going to go down on the left. And these things are enough for me to know what's going on. I go from increasing to decreasing here. Means I have to come through here like this. So here's our graph. I stay concave down until I get to this, where I switch to being concave up, and I'm still decreasing. And then I have to approach this horizontal asymptote. So something like this is what our graph has to look like. I know this isn't perfect art, and I'm not expecting perfect art from you guys either. But I do want to see you trying to draw good graphs and doing it by hand. Now, the shitty thing about WebAssign here, I mentioned it at the start, is that it just has you select the right graph from a collection of graphs. Here's the point, 0 comma 0. That's not going to help you practice this. As you solve those homework problems, you need to go through this procedure like I did here. Let's take a look at the actual graph of this function. See what Desmos does by plotting thousands and thousands of points. y equals x times e raised to the negative x. Boom. Oh shit. Look at that. Look at that. This is not half bad, is it? Where's my max? It's at 1 comma e to the negative 1, right? Look at that. There's your max. Found it. Where's your inflection point? It's at 2 comma 2e to the negative 2. Boom. Look at that. There's your inflection point. Not half bad, right? The shape is correct. The end behavior is correct. The max is correct. The inflection point is correct. The intercepts are correct. The asymptote is correct. This is what I want to see from you guys. And I respect that it's challenging. I respect that it's not a simple thing. It will take practice. I'm not expecting perfect art. If you gave me this graph on an exam, full credit, 10 out of 10, perfect. No complaints. We are increasing concave down, decreasing concave down, decreasing concave up. As long as I can tell whether you're increasing, decreasing, concave up, concave down from your picture. You have your maxes and mins labeled. You have your inflection points labeled. You have your intercepts labeled. You have your asymptotes drawn in and labeled. As long as you have all of that, I will give you full credit. But you need to practice this, and you need to do it by hand as you practice it. Don't just pick the correct graph from WebAssign. It's not the same thing. Questions on this procedure? It looks like we may actually have time to do another one. In the interest of getting as many examples in as we can, I'm going to go ahead and grab one more out of the textbook. I'll make sure it's a quick one. Simple. How about any one of these? The odds you can look up in the book. Let's do this guy. Or actually, fuck it, yeah, let's do this guy. I'm going to do number 4. That's down sketch. Y equals x to the 4 minus 8x squared plus 8. The domain, this is a polynomial. So all real numbers, negative infinity to infinity. Intercepts. Well, the y-intercept always comes from plugging in 0. F of 0 here is 8. Right? 0 to the 4 minus 8 times 0 squared plus 8. X-intercepts, we're going to have to do some work. If I want to set that thing equal to 0, that means I have 0 equals x to the 4 minus 8x squared plus 8. And this we can factor, but we have to be a little bit clever. It's not a quadratic, right? The largest power here is 4. But you notice all the powers are even, which means you can make a little substitution. U equals x squared. And that means u squared would be x to the 4. So this piece here is the same as u squared minus 8u plus 8. And then I can try to factor this. So I need two numbers that sum to negative 8 and multiply to positive 8. That would be u minus 4 times u minus 4. So that's x squared minus 4 times x squared minus 4. Now I go back to my x's. And this is x minus 2 times x plus 2. And it shows up, each of those show up twice. X minus 2, x plus 2. So in other words, this is x minus 2 quantity squared times x plus 2 quantity squared. This is a nice trick for factoring. Oh, you're right. Wait, no. I think you're right. Yeah. You're 100% right. Yeah, that's not how this, I'm so sorry. That's not how this factors. Yeah, they have to multiply to 8, not to 16. You're 100% right. Yep. Sorry. Trying to work too fast. Okay. So how does this factor? Please tell me this factors nicely. So two numbers whose sum is -8 and whose product is +8. Those might not exist, actually. Let me see. Well, 8, yeah, 4 and 2, no. It's not correctly. Fuck me. Yeah, this might be a little bit more savage than I thought at first. It is, isn't it? Yeah, how does this factor? It doesn't factor nicely, huh? Ah, shit. So, yeah. We can complete the square. That's going to be a little bit tough. We can use the rational roots theorem if you remember that. I guess that's an option. So what is, let me compute my discriminant here. B squared minus 4ac is going to be 64 minus 4 times 1 times 8, which is 64 minus 32, which is 32. That's positive. So there are real roots here. So what are these going to be then? 32, is 32 a perfect square though? It's not. So they're going to be irrational roots, at least in terms of u. Okay, so this is not necessarily easy to factor. So we would use something called the rational roots theorem. You guys remember that from pre-calculus? That's where you come up with your list of p's and q's. Damn, I was hoping this would be quick. P's are divisors of the constant term. So it's plus minus 8, plus minus 4, plus minus 2, and plus minus 1. The q's are divisors of the lead coefficient, which thankfully is just plus minus 1. So then if you have any rational roots, they must be of the form p over q, where p is one of these numbers and q is one of those numbers. We can check one quickly. Yeah, so we're not actually going to use this substitution trick here because it doesn't factor like that. If you plug in 1, you don't get 0. If you plug in -1, you don't get 0. So I can cross these off. We can check f of 2 using synthetic division. This would be 1, 0, -8, 0, 8. 2 times 1 is 2, 2 plus 0 is 2, 2 times 2 is 4, 8, and -8 and 4 is -4. 2 and -4 is -8. Plus 0 is still -8. 2 and -8 is not 0. Damn. It's -16. -8. So 2 is out. We can check -2. 1, 0, 0, 8. I may have to take back what I said about being able to do a second one of these. We're going to get hung up just finding the x-intercepts. It's going to be +4. We're going to run into the same problem here, aren't we? Yeah, this isn't going to work.
Quadratic formula.
Say that again?
Wouldn't it better use a quadratic formula?
Well, you could try to use the quadratic formula in terms of the variable u here. Yeah, that would work. But because the discriminant isn't a perfect square, we're not going to get, the roots are going to be irrational in terms of u. And then you could square them to get the roots in terms of x. Sometimes this is quicker. So I was hoping that we would be able to get a rational root out nicely like this, but I don't think it's going to work. This would be -4, which would give me +8, which would give me 8, which would give me -16, -8. So the 2's are out. um, which means it must be 8 itself, because 4 is a square, which would mean that in terms of u. So let me just check 8 real quick. 1, 0, -8, 0, 8. Bring down the 1, and this is 8. 8 times 8 is 64. 64 minus 8 would be 56. Oh no, this isn't going to work either. 8 times, no, fuck this. All right. God damn it. Really wanted a nice example for you guys. So we're back to solving this. We can try, Julio's suggestion is not a bad one. So let's rewrite this as the quadratic and try using the quadratic formula. That would mean u is equal to 8 plus or minus the square root of 32. I computed that earlier, the discriminant, all over 2a, which is just 2. So this is 8 plus or minus 32 is 2 to the 5th. So that's 2 times 2 to the 4. So this is 8 plus or minus 2 squared times the square root of 2 all over 2. This really just kind of sucks though. This is 4 plus and minus 2 root 2. And these are u values. So that means x is the square root of these. It would mean that, yeah. So it means my x's are the square root of 4 plus root 2, the square root of 4 minus 2 root 2, 2 root 2. And then they're negatives also, negative square root of 4 plus 2 root 2, and negative square root of 4 minus 2 root 2. I'm inclined to not trust this either, I think. So I want to just check something really quick. And this happens when you get nervous and you're trying to do algebra quickly. So just to make sure I'm not going crazy, we have 4 roots here. Are they these nasty motherfuckers? They are. Ugh. All right. So we were correct. It's these. Okay. So here are our 4 x-intercepts. They're all pretty horrific looking. If we move on from intercepts, I'm just going to say, this is positive. I'll call this x. 1, x2, x3, and x4. Symmetries. We do have symmetry here. F of negative x would be negative x to the 4 minus 8 times negative x squared plus 8. And when you raise negative x to the 4th, the negative goes away. That just becomes x to the 4th. When you raise negative x to the 2, that just becomes x squared. And this is the same as the original function. So this means f of x is even. So we have y-axis symmetry. From there, asymptotes, it's a polynomial, so there are no asymptotes. But we know what the end behavior is. So the lead term in this polynomial is x to the 4. So my end behavior is going to be up on both sides, whatever crazy bullshit goes on in between here, be up on both sides. So as x goes to negative infinity, y will be going to positive infinity, and as x goes to positive infinity, y will be going to positive infinity. And now it's time for the derivative stuff. So increasing, decreasing, and mins, maxes. Hopefully the polynomials that we have to work with here will be a little bit nicer. The derivative of this function, f prime of x, is 4x cubed minus 16x, which certainly is easier to work with. This is 4x times x squared minus 4, which is 4x times x minus 2x plus 2. So my number line for f prime has -2, 0, and +2. -2 coming from this factor, +2 coming from this factor, 0 coming from this factor. If I test over here something to the left of -2, like -3, I would have negative times negative times negative, right? All three of these terms would be negative. This would be -12, this would be -5, and this would be -1. So 3 negatives multiplied together, that's negative, which means my function is decreasing here. Between -2 and 0, I could test x equals -1. This piece would be negative, this piece would be negative, and this piece would be positive. Negative times positive is positive. So my function is increasing here. You can use the multiplicity trick to fill in the rest of this. Since we are short on time, I'll do that. Or you could test points, it's up to you. It will be decreasing and then increasing. Each of these are multiplicity 1 factors. You could test x equals 1 here, test x equals 3 here, and you'll find that this is the pattern. So I know I have a local min here, a local max here, and another local min here. So x equals 0, I know that this point is 0, 8. That's the point on the original when x is 0. To find the points here and here, I need to know what is f of -2. So if I take -2 and I plug it into the original expression, I get -2 to the 4 minus 8 times -2 squared plus 8. -2 to the 4 is +16 minus 8 times 4 is 32 and plus 8. So what is this? If I take 16 minus 32, that's -16. -16 plus 8 is -8. So f of -2 is -8. So this point over here is -2, -8. And then by the symmetry, I can say that the point over here has to be +2, +8. Right? F of 2 is equal to f of -2 by my symmetry. So I've got all my local mins and local maxes. The last thing I need to do is come up with my concavity information. To get that concavity information, I differentiate again. I hope you don't mind me eschewing the labels here. Just trying to move quickly. F double primed, I take the derivative of the derivative, I'll get 12x squared minus 16, from which we can factor a 4, and I get 3x squared minus 4. So f double prime will be equal to 0 if this is equal to 0. you divide over the 4, you just get 3x squared minus 4 here. So that's the same as saying 4 is equal to 3x squared, or 4/3 is equal to x squared. So f double prime is equal to 0 if x is equal to 2 over the square root of 3, or negative 2 over the square root of 3. We just take square roots on both sides. So on my number line for f double prime goes those two numbers. Negative 2 over root 3. Positive 2 over root 3. If we test something to the left of this, we need to know about how big this is. The square root of 3, 2 squared is 4. So the square root of 3 has to be smaller than 2, which means 2 over the square root of 3 has to be bigger than 1. But it's definitely not bigger than 2, right? That would be like 2 over 1. So we could test x equals negative 2. If you wanted to be safe, test x equals negative 3 or negative 4. If you plug negative 2 into this second derivative, you'll have 12 times 4 minus 16, which is 48 minus 16, which is definitely positive. So we're concave. This is the number line for f double prime, remember. So we're going to be concave up here. Between these two, we can test 0. If you plug 0 in for x, you get negative 16. So f double prime is negative there, will be concave down. And to the right of 2 over root 3, you could test x equals 2. And again, this is an even function right here. The second derivative is even, so you know you're going to get the same thing you would there. This is going to be positive. So back to being concave up there, will be 48 minus 16 again. So putting all of this together into the number line, giving us the shape of f of x. I want to put all the numbers from past number lines on this. So those will be negative 2, 0, 2, and these guys. So if I do that in order, over here would be negative 2, and then negative 2 over the square root of 3, then 0, then 2 over the square root of 3, and then positive 2. To the left of negative 2, we are definitely concave up and decreasing. So concave up and decreasing looks like this. Between negative 2 and negative 2 over the square root of 3, what's going on? Well, at negative 2, we switch from decreasing to increasing. And at negative 2 over the square root of 3, let's see, so everywhere to the left of that point, we're still concave up. So we're still in here, concave up. But now we are increasing. That looks like this. At negative 2 over the square root of 3, we switched to being concave down. But we're still to the left of 0, so we're still increasing. So now we are concave down, increasing. We look like this. At 0, nothing happened to our concavity, so we're still concave down. But we did switch from increasing to decreasing. So now we're going to be concave down, decreasing. At 2 over the square root of 3, our concavity changed from concave down to concave up. And we are still decreasing because we have not yet gotten to 2. So now we are concave up decreasing, which looks like this. And then finally at 2, we switch to being increasing, but we are still concave up. So that looks like this. So fairly complicated problem here, even ignoring the weirdness with those crazy x-intercepts from the start. If I want to draw this graph, we do the same sort of thing. We plot the points that we know. Unfortunately, some of these x values are really weird, but that's why I just called them x1 through x4. Where did I record those crazy ass numbers? Yeah. So x1 through x4 were these like nasty numbers we got here. The most negative of which was x4. I'll put that out here. And then x3 was also negative. x2 was positive. And x1 was the large positive one. The other things we have are -2, 0, and 2. Let me see, so our y-intercept was up here at 0, 8. And then I need to know about how big these numbers are. That's a little bit unfortunate. But this first guy, x1, is the square root, the square root of something a little bit bigger than 4. So this is definitely bigger than 2. This is the square root of something smaller than 4, right? We take 4 minus this and then take the square root. So this is going to be a little bit smaller than 2. And these are the symmetric points. So this is going to be a little bit to the left of -2. And this guy is going to be a little bit to the right of -2. So where is 2 and -2 regarding all of these? x1 is bigger than 2. This guy, so 2 is going to be somewhere in here, which means -2 is somewhere over here. And then 2 over the square root of 3, I don't know where those are with respect to these. So let me see here, where is that? 2 over the square root of 3, we are going to say, let's see, these are x-intercepts, right? That's what they are, they're points on this graph. 2 over the square root of 3 is definitely bigger than 1, but smaller than 2. That's what we said. So we're going to say -2 over root 3 is here, and +2 over root 3 is here. All right, I think we are ready to do this, lads and ladies. We can draw our picture now. -2, -8 was the point on the graph here. And +2, +8 was the point on the graph here. So we know that we have a min here and a min here and a max here, x-intercepts here and here, here and here, and we know our end behavior is up on both sides. So let's start trying to do this. We are concave up everywhere over here. Let me do my best to draw this in a way that's not ugly. And then I know I have an IP here. So somewhere around here, I switch to being concave down. I'm going to try to draw that. This is my IP. In a way that makes sense. And we do the same thing over here. We have an IP here. And then we change our concavity back to being concave down, which we stay throughout the rest of this. I know that this was horrifically rushed, but I hope it gives you a feel for what it is we're doing. Please don't stress too much about the really weird x-intercepts that we found at the start of this. These are indeed very, very strange. And I wouldn't do that to you on a test, but they make for reasonable homework problems because you can think about these things carefully and how large or small they should be. You can use a regular 4-function calculator if you want decimal expansions for those. I'm fine with that. The main thing is finding mins and maxes, finding inflection points, finding end behavior, and knowing what it looks like when you string all of those pieces together with appropriately shaped pieces, right? Increasing concave up, decreasing concave down, all that shit. I am sure that we are out of time now, probably have gone. Oh, no, we didn't, barely went over. Look at that. Okay. Again, I apologize for how rushed that last example was. These problems take a while. That's what I was saying at the start, right? I didn't even expect us to get to do a second example today. So I'm glad that we were able to do that. Please run back through this one on your own. Run back through this and take your time. Feel free to use a non-graphing calculator to get decimal versions of these numbers or those really nasty roots, right? So this guy, x4 here, was negative square root of 4 minus 2 root 2. That's a horrific number. X3 here was negative square root of 4, or sorry, this one had the plus, and then this one had the minus 2 root 2. X2 was positive square root of 4 minus 2 root 2. And x1 was the square root of 4 plus 2 root 2. Numbers like these do show up as roots of polynomials. Finding roots of polynomials is tough. It's not a simple thing. But I think this was probably the hardest part in this whole goddamn thing, was finding these numbers and having some idea of how big they were. So run back through this problem in your own time and make sure you understand everything we did. You may also run back through that first example, but there's a homework up now that has plenty of problems for you guys to practice, most of which are polynomials. They're not terribly hard to work with, but some do involve rational functions and other slightly more complicated things. I'll be posting the video from my earlier class to your page as well, so you can see the rational function example I did with them. And yeah, that's all I have for you guys here today. On Wednesday, actually, let's see, is Wednesday another student teaching day? I might be getting close here. Yeah, Katie had a thing this week, right? So, curve sketching. Oh no, yeah, we're gonna start talking about applied optimization. Probably Wednesday, I'll do a little bit more curve sketching, at least one more example here. And then we'll start talking about applied optimization, which is an interesting and challenging thing. And we'll move from there. Remember, your exam is going to be the day you get back from spring break. And before, thank you, Kevin, before spring break, I need everybody to come by an office hour and at least tell me what you've done so far on your project. Just a little check-in to make sure that you're not doing nothing. If you haven't done anything for your honors project yet, you need to begin your research now. It's really important. These are big projects, and they're meaningful to the honors program. If you want to stay a part of the honors program, you need to perform on these projects. It doesn't need to be anything huge and amazing, but it does need to be some legitimate research looking into the things that you said you were going to look into. So Kevin, it's not, I don't have like assignments for you to check off or anything like that. I just need you to come to an office hour between now and the start of spring break and tell me what you've done so far, where you're going, and what sort of materials you're putting together for your honors project. That's all. Alrighty, guys, I'm going to go ahead and end the recording here. I hope you have a lovely rest of your day, and I'll see you on Wednesday.